Okay, so here's where we were last time. We were doing some field map drawings, and the objective here is to, instead of calculate exactly numerically what is the size and direction of an electric field at any one point, we want to kind of zoom out, see the forest for the trees, as they say, and try to figure out just a kind of a more holistic picture of what a field looks like around some charge configuration. And the one I picked to do first is a very important one. It's called the electric dipole. So I have two equal and opposite charges, and I've colored them red and green simply for the purposes of identification. I've put each of their own field lines in there, and those are the familiar radial ones. This is a positive, so it's radially away, points radially away in all directions. And this is a negative charge, so it points radially towards. But of course, either one of those alone is not the whole picture. We actually have to figure out the net electric field. And at every point in space, we're going to have to do the vector addition of what both of them contribute. So we have to figure out what does the red plus the green mean. Now, if you're thinking vector addition is enough of a pain to do at one point, we have to do it at every single point, well, obviously we're going to have to look for some tricks or some symmetries so that we're not here all day. In order to do that, let me go ahead and appeal to this equation. This is the equation for the electric field made by one charge. And basically, we're going to try to figure out how to take the features that it already has, that we already know, and make it so that it's faithfully represented in the drawing. So for instance, one of the things we know is that if you go further away from a charge, its electric field gets weaker, right? In fact, it's an inverse square law, right? If you double the distance, the field will drop to 1/4 of its previous value, right? You can say things like that. And so, I'm going to use that to my advantage. And the other thing I do want to point out is that if you increase the charge, the electric field increases, all else being equal. So if you're at equal distances from a bigger charge, you'll feel a stronger field. Now these two are directly proportional. Which means that, of course, if you double the amount of charge, you're going to have twice the strength of the electric field at the same distance, just as an example, right? Or if you have 3 times the charge, you'll be 3 times the field strength at the same distance, so on and so forth. So let me take a look at how to make sure that both of these are faithfully represented in our drawings. In our drawings, let me remind you that line density is a proxy for field strength. So that is how we look at a drawing, and we can tell where the field is stronger or weaker. If the lines are closer together, the field is stronger. If they're further apart, they're weaker, right? So first, let me talk about this thing about charge. So let's say I have a plus Q. Now, I've been typically drawing 8 lines out of a charge, right? So I've been drawing 1, 2, 3, 4, 5, 6, 7, 8. That's, of course, just a sampling. It's not like the electric field is everywhere, but that's just a way to draw it, right? Now, that's just a decision I make. So let's say I choose to draw this charge with 8 lines representing it. The only charge you have the freedom to do that with is the very first charge in the map. So the very first charge you lay down. Let me show you why. So let's say if you choose 8 lines to represent that charge, you no longer, for any subsequent charges, have the freedom to just draw however many lines you want. Here's why. Let's say I have a charge which is twice as much as that first one. I can't just draw 8 lines out of that one too. Here's why. If I draw 8 lines out of that one, Well, if we looked at a given distance, let's say this distance, whatever far away that was, we have a bit of a problem. And the problem is with the line density, right? Because I chose to draw 8 lines out of both of those, the line density is the same at the given distance. Why is that a problem?
Not representative of the change.
It's not representative of the fact that the electric field should be twice as strong. So how do we rectify that?
Draw more lines.
We draw more lines, exactly. So we know the field is twice as strong at a given distance, and so we need the field line density to be twice as much, so we have to draw twice as many lines. Okay? So if you choose 8 lines for your first charge, then if you double the charge, you have to double the number of lines. This is the scale of your map. Okay? So the scale of your map is that there is a certain correspondence to the charge versus the number of lines. Okay? And you want to respect that. You pick a scale for your map, but then the amount of charge being different means the number of lines that is attached to it has to be different. It's the same way as when you're drawing a map of anything, right? You're drawing a road map. You want to pick that, say, 1 inch represents a mile. How useless would that map be if 1 inch was a mile on this part of the map and 1 inch was 3 miles on this one? It'd be all warped and weird looking, right? Then you put a big disclaimer on the map that says not to scale, right? Because you're just willy-nilly drawing everything. So you want to pick a scale for your map, just like you pick like 1 inch as a mile. You want to then have 1 inch meaning a mile everywhere, and this is our way of making sure that you do that. Now that doesn't mean you have to, there's no universal scale. You pick the scale, okay, but you have to be consistent. It has to be consistent throughout the map. I'll say consistent throughout one map. It doesn't have to be the same as another map, right? So you might have one map of a city and one map of a country. Obviously 1 inch is not always going to be 1 mile. Otherwise, if you want to make 1 inch be a mile in the city, if you also want 1 inch to be a mile in a map of the whole country, that's going to be a huge map, right? So different maps can have different scales, but on a given map, you should respect the scale everywhere on that map, right? Does that make sense? Okay, so it's consistent throughout one map, but not necessarily every map, okay? So keep that in mind. It just has to be consistent along one drawing. All right. So, how does that apply to my problem? Well, in my problem, I have that these two are both the same amount of charge. So if I choose to represent this with 8 lines, then this has to be also represented by 8 lines, right? So in my case, I get to draw the same number of lines on each one, but that's not because that's what you always do. It's because it happens to be true here. So be aware of that for other maps you might be looking at on the homework, for instance, that you can tell a lot about how much charge something has by looking at how many lines it has attached to it. Okay? So, I'm going to pick my scale is that these lines are going to be 8 lines each for my plus charge and my minus charge. You could pick 16 for both, it doesn't matter. The thing is just once you pick something, you have to respect it for the other charge as well. Okay? Because they're the same amount of charge, so same amount of lines, whatever you want to pick. Okay, so that's one thing. I already took care of this one, like the Q factor, so to speak. Are there any questions on the scale part before I clear myself some room? Okay, so let me clear myself some room. And the next thing I want to do in my vector addition, I want to take a look at that R factor. We know as we get further away, the electric field gets weaker. Well, let me suppose the opposite. Let me suppose that the distance gets really small. What happens to electric field strength? It goes really high, right? In fact, in the limit that r goes to 0, it goes to infinity. What can compete with infinity? Nothing, right? So here's what we have. If we are really close to, say, charge 1, then the net electric field kind of looks like this. When you're right next to charge 1, that's really the only thing that matters, right? So we can completely assume that the other charge starts to not really matter. And so here is where I'm going to come in, not with a dotted line, but with black, coming in to sketch E net. And one of the first things I can do is just trace very close to one charge. E net is basically indistinguishable from the electric field of that charge alone. You're right in the face of one charge, the other one makes a negligible contribution, right? And same thing with the other one. When I'm really close to the green charge, that basically dominates E net. So there's my first sketch of E net coming in with the black color, which is going to be the vector sum of the two. When you're really close to one charge, the other one makes a negligible contribution in comparison. And I've drawn 8 lines out of both here because the amounts of charge are equal, right? Are there any questions on that? Okay, so that's something that I can't draw out to infinity because obviously when I start to get over here where you're roughly equidistant from each charge, then the red is not going to hugely dominate the green or vice versa. They both start to matter, okay? So now we're going to have to get into vector addition where we can't just ignore one contribution completely. Let's look at the line between them. That's the easiest because both of the electric field lines point the same way, right? So the red points to the right because that's from the positive charge, so electric fields contribute away from positive charges. And the green also points to the right because that's made by the negative charge, and negative charges make electric fields toward them. In both cases, that happens to be the right, so there's no question whatsoever about what happens between them. The net electric field between them is definitely to the right, okay? Let's continue by looking at the line running through both charges. So this horizontal axis here. Over here we have a rightward contribution and a leftward contribution. Are they going to cancel and go to 0? No. Why not?
Because you're further away from one.
Exactly. You're further away from one and closer to the other. So whichever one you're closer to is going to win. In this case, I'm closer to the green charge. So the net electric field is going to be dominated by the green. So that's to the left. Now I'm not saying it's as big as it would be if the red charge weren't there. The red charge has taken a chunk out of it, but it still points to the left. Remember, we're just trying to do this just roughly speaking. I'm not trying to claim it's the exact same magnitude. I'm just trying to claim that it still goes to the left. And just like over here, it's going to point, it's going to be dominated by the red, because you're close to the red. The green certainly takes a chunk out of it, but the green can't win, right? Because the green charge is further away. So that takes care of the line along which the charges run. And now we have to move off of that axis and start to get to where the contributions are more diagonal, right? So we again look for some sort of symmetry, and what I will suggest is a symmetry axis called the perpendicular bisector. So the axis that runs perpendicular to that line, and by bisector I mean that it's exactly running halfway between these two charges. So that line is equidistant at all times from both charges. It's not closer to one than the other, okay? Does that make sense? Okay, so let's pick a point on that bisector and imagine what might happen. Let's say right here. So there we have a radially away contribution from the plus charge, looks like that. And we have a radially toward contribution from the negative charge, it looks like that. Now I drew those the same size. I tried to anyway. How do I know they're the same size? Same distance from the same amount of charge. That's the advantage of the perpendicular bisector, is that I know that the sizes of electric fields are exactly the same. What about the direction? What does the direction look like? What if you did the vector addition of those two, what would you get?
Exactly to the right.
Exactly to the right. Now, for those of you that might not see that, let me sketch out what is the consequence of having one contribution like this and one contribution like this of exactly equal size. If you break it up into x and y components, you see that they reinforce in the x direction, but they exactly cancel in the y direction, right? Because they're equal angles, but one is above horizontal and one's below horizontal. So the y contributions cancel while the x contribution reinforces, and that is how you end up with E net being to the right. And by the way, notice that that argument holds everywhere on the bisector. So the net electric field will always be running to the right anywhere along this line. The only difference is that the electric field gets weaker as you go further along this line away from both charges, right? So we might draw that like this, right? It's weaker over here. So drawing in a couple examples here. We're drawing the net electric field through the bisector. We're just drawing it a bit weaker as we get further away, right? Because you're just getting further away from both contributors, right? Now at this point, I'm going to say that we have enough to play connect the dots. So let's go ahead and start doing that. So if I'm going to connect, I'm going to get something that looks like this. Get this kind of low-B shape, okay? So that right there is E net. That is the net electric field that results from the vector combination of both contributors. And just to make it a little bit more clean, I guess I suppose I can do a little bit of a sketch for you over here that doesn't have the underlying red and green. So here's my plus Q and minus Q. Basically, it looks like this. That's a sketch of the net electric field. I want to point out a few of the features that you can see here. First of all, I have tried to respect the line density. So the line density, I guess let me draw a few more here. These are the loops that are so big that I can't really, of course, fill them in. Dot, 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 but they're these kind of loops. So I want to point out these following features. I want to point out that the electric field between them is very strong. Why is it strong? Well, of course, you're right next to both charges, and when we said when you're between them, they tend to point exactly or almost the same way, right? They point exactly the same way on this line, and then when you're not too far off that line, they're going to point progressively, or they're going to point sort of in the same direction. As you start to move off on the perpendicular bisector, the two contributions, they start to have significant components that cancel, right? Because the y components cancel and only the x components are left, and you're just getting further away from the charges in general. So the electric field should get weaker as you go out here. And I've tried to show that by showing the field lines getting further apart. So the line density is getting more sparse. So basically, this charge configuration has a strong field in the region kind of between them, and then it starts to get weaker as you get further away in any direction, either because the contributions start to be more canceling, or you just start to be further away in general, so the contributions are smaller, right? The individual contributions are smaller, and or they're canceling more with each other. Okay? Are there any questions on that? Okay, so this is a field that we use quite a bit. Electric dipole comes up, it's a useful charge configuration. I want to do one more map for you, okay? And I want to do a map for you which is kind of in some ways like the flip of this one. This is a very simple charge configuration. It's just plus charge and minus charge, but the map looks very complex. I want to show you the simplest electric field possible, but it's the charge contribution that makes it is kind of a weird, contrived, complicated charge configuration. Okay? So, any questions on this before I clear some space? Okay, so I want to show you the electric field map of what's called a infinite parallel plate capacitor, or sometimes I'll call it a CAP for short. Now the fact that it has a name kind of gives us a preview of what we'll be doing around homework 4. It's actually an electronics component. But for right now, we're not interested in what is this functional ability in an electronic circuit. We're interested in as just a configuration of charge. So what is it? It's basically a plane of charge. Infinite plane. So imagine if you had a sheet that went on in every direction, and it was just covered uniformly with charge. Now obviously I can't draw very well, so I can kind of draw the dot, dot, dot to show that it extends vertically. You're going to have to imagine there's also a dimension that comes out of the board as well. So it's not just an infinite line, it's an infinite plane. Okay? So, what use would I have with this contrived charge contribution? Obviously this charge distribution doesn't really exist. The universe is not infinite, so there's no such thing. Infinite plane cannot exist, but there are very long ones, large ones, right, that this will be an excellent approximation for. So let me pick a point that's close by like that. And let me just get a flavor for what is contributed by the various charges. Let me pick a charge right there. Obviously that's important because it's immediately to the side. So that's going to contribute away. That's going to be directly to the right. And then let me pick just a representative pair of charges whose significance is that they're symmetrically to both sides. So let me say pick this one and pick this one. Right? Now, obviously there are more, but these two that I've just circled are emblematic of every pair, right, that runs along this thing. So let me draw contributions away from those guys. So away, away, it looks like that. So that's what those three charges contribute. You can probably already tell which way the net field is going to point. Which way is the net going to point? Directly to the right, because the two diagonal ones, the vertical or y contributions are going to cancel. So the net field is going to be to the right. So the E net is going to point that way. E net. Then what I want to do is I want to take a look at those same exact three charges and take a look at them further away let's say a point over here. Now, one thing you can, of course, say right away is that all of them are going to make smaller contributions, right? You're just further away from each of the three charges I've earmarked. The plus one still points to the right, but it's smaller, right, because you're further away from it. And all of the other two, they will also contribute smaller overall, and they will point directly away, so it looks like this. And of course, we can make the same argument that E net is going to point which way? Still to the right. Now here's the counterintuitive part. E net still points to the right, for sure. Do you think it's going to be bigger or smaller than this? You think it'd be smaller. It's not, though. Here's why. Even though all of these three contributions are smaller, notice that the steepness of the angle, right, these two here were like this, so they could be very large but mostly cancel. But now that we go further away, they're a bit more like this, right? So it turns out that if you worked out the math, and I'm certainly not going to do that because it's really ugly, I'll just tell you what the result is. It turns out that the fact that these arrows are smaller is exactly made up for the fact that they're more pointed forward and they don't cancel each other as much. Okay, so what happens here is E net is actually the same size. It's the exact same size as well as direction. The size part is, of course, the surprising part. So I'll put a little exclamation point there in parentheses. And again, the explanation for this, if you work it out very carefully, is that even though each contributor is smaller, they are all more forward and therefore reinforcing. Those two things exactly make up for each other. In fact, it turns out that you also have to bring in the contributors that are not just along the plane, but also, along the, that are on the board that I've drawn here. You also have to contribute for the, have contributions that are in the plane that you can't see. But the point is that even though each individual contribution gets smaller when you go further away, they're more made up by the fact that they're more forward and more helping each other. Okay, so the analogy I use for this, okay, this is like the rich neighborhood, right? No one knows their neighbors. Okay, everyone has a lot of money, but then they just use that to like fight each other or whatever. Okay, that's like these two contributions. They're both very large, but they almost add to zero simply because they're almost opposed. This is like the neighborhood. Not everybody has as much money, but they help each other out, right? They're more collaborative, right? Hey, I watch your kids while you go to the store, things like that. So it ends up being that the net sum of the two is that the electric field is exactly the same. This is the simplest electric field possible. It's an electric field that never changes. Let me draw it. It looks like this. I'll draw it over here. It goes like this. And the fact that it never changes size is represented by the fact that the spacing of the field lines never changes. This is the simplest electric field possible. At any given point, this one, or this one, or this one, it's exactly the same. We give a name to this. We call it a uniform electric field. A uniform electric field is one which has a constant size and direction everywhere in space. Once you know what it is in one place, you know what it is everywhere. You'll notice this mentioned several times in the homework. This is basically when I want to throw you a softball and just tell you the simplest electric field possible to work with so that that's not a stressor on the problem. What's causing that? Well, this is the cause of it, but often because we're cleaving apart cause and effect, we couldn't care less about the cause if we're someone hands you the electric field on a silver platter, just use it for finding the force or whatever you're asked, right? You don't always need to address it from beginning to end. You can talk about just what's the cause of the electric, you can just say, well, these charges make this electric field and not have to worry about them acting on something, or someone can just hand you an electric field on a silver platter and then you can find the forces. You don't have to do it from beginning to end in every problem. So you'll find many of the problems on the back half of your homework number 1, they just pick one. They either ask you about what field do these charges make, or they just hand you a field and ask you what forces it'll exert on something, okay? So, let me go ahead and use this. I have one infinite parallel plate capacitor, or sorry, well I guess I should say that this is just an infinite plane of charge. To build up to the parallel plate capacitor, you just have 2 of these. It's like a dipole. So we just have one positive plane and one negative plane. So let's draw that. Are there any questions on anything here before I clear a little space? Yeah.
So what if you put the dot between the space between each class?
I'm sorry, I'm not following.
So for that picture, you put the dots straight, horizontally next to the, what do you call it, plus.
Right. But I mean, this could be anywhere along the sheet. You could make this argument, right? If I were over here, right, I could make that same argument by thinking about the charge immediately to the right.
So you can't.
And then also, every charge that's on the side would be paired up. Remember, it's an infinite plane, so you'll always have pairs running from right next to it all the way to infinity. And that's your argument for the fact that the electric field will always point to the right.
So you can't put a dot between those plus signs.
You can't put a dot. What do you mean a dot?
The black dot.
You can put it anywhere you want to make this argument.
Yes, but between the space of those.
Oh, here?
Yeah.
Yeah, I mean, then you're right on top of a charge. So that's a whole different story, right? Like I'm never going to ask you to find the electric field like when you're actually sitting on charge, right? You have to be away from it in space. So remember, this whole thing is filled. It's uniformly smeared with charge. There's no gaps at all. I just can't draw that. I mean, if you want me to just draw plus, 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 and it seems like there's no gaps anymore, right? But there's no gaps there, right? It's like, buttering a piece of toast, right? Okay, there's no gaps between in the butter, okay? It's just a smear of charge. Was there another question somewhere? Okay. So, here's a parallel plate capacitor. There's a plus and a minus. These are both infinite planes. Let's take a look at what the electric field would look like for that. So let me attack it the same way as the dipole. Let me label them. So I'll label the plus to be red. And I can draw the electric field. That makes a uniform electric field. It looks like this. Everywhere out in space. Uniform. Simplest electric field possible. And then I'll go ahead and do the negative infinite plane. I'll put that in green. How does the electric field look like for that? It's uniform as well, but towards it, right, instead of away. I can draw that. Looks like that. All right. So what happens with the electric field between the two plates or planes? Does it reinforce or cancel? Reinforce. Is the field going to be uniform still? Yeah, two uniform fields makes a stronger uniform field. So the net electric field goes like this. I might draw it twice as dense, in fact, just because it's being reinforced double by the fact that I have two plates. And here's the tricky part, the outside of the plates, okay? So if we're, let's say, out here on the left, we're closer to the red plate, right? So you might think that the red one wins, except it doesn't. They exactly cancel. Even though you're further from one plate and close to the other. Why is that?
Because it's always constant.
It's constant anyway, so you lose, the electric field doesn't die with distance. So it doesn't matter now that you're further from one plate than the other. The contribution that each plate makes is exactly the same going out to infinity, so it doesn't matter if you're closer or further or anything. So these guys exactly kill each other. The electric field is zero on the outsides. It's uniform in the middle, and then it's zero on the outsides.
What would be the equation for, say, the force inside?
The electric field inside?
Yeah.
I don't want to tell you because it's beyond the scope of the class.
Okay.
Yes.
Fair enough.
It's just uniform. That's basically what you need to know. And if I need you to know it, I'll tell you the number or something like that.
Okay.
It may be in your book, I don't know, but I'm going to skip it anyway.
Fine with me.
Okay. So there's the two field maps that we have so far. We have the electric dipole, we have the infinite parallel plate capacitor, and now let me fill in the missing link, okay? Because there is a beast that is halfway between these two. So if we took these two, this dipole, and that's of course just 2 point particles, and then we imagine that these point particles are like Play-Doh, and we smush them and we stretch them out into a small plate. We have what's called the finite parallel plate capacitor. It looks like this. So this is all called the finite cap. It's the missing link in the evolution between the two, okay? And that has features of both. The electric field of that, well, when you're between the plates, it looks very similar. You don't notice the edges, it looks very close to uniform. But then as you start to run off the end of the plates, you start to notice the fact that, of course, you have far more charge on one side of you than the other. It's not like an infinite plate where you always have charge equally to both sides no matter where you are. So then it starts to have this lobe shape. It starts to look like point particle one, okay? So it's like a hybrid of both. When you're between the plates, it's approximately uniform. It's not perfectly uniform anymore, but it's approximately. Because if you're hanging out between the plates, you roughly have charges to equally all around you, and you don't necessarily notice the edges. But then it looks kind of more lobey, I guess, if that's a word, has these kind of lobes or loops, okay, on the outside. So it's kind of like the marriage of the two, right? The dipole, the point particle dipole field map, and the infinite cap map. Okay? And I guess I should say over here, the electric field, we know that it was weaker out here. It's even weaker out here. Right? And of course, in the limit, that those planes really go infinite, so if we not only smush those point particles into Play-Doh, make them into small plates, but then take those plates and run them all the way to infinity, it not only gets weaker, but it goes perfectly to zero, okay? So this is kind of like your evolution, right? You see the classic picture, I think it's called Evolution of Man, right? It shows like fish kind of getting up and and then have a briefcase at the end. Okay, so this is, we start here, we smush the 2 point particles into finite sized plates. This has features both of what's to come and where we came from, and then by the time we get over here, we have the plates stretched to infinity, which makes this a very simple electric field. The reason why I've gone through this evolution, and obviously this is very conceptual, is because we will have very similar kind of evolving field maps later, especially for magnetism. So I'm going to literally say, hey, you remember this, then this, then this? Well, here's the magnetic analogy, okay? So it helped. By then, these are familiar, and we can help to introduce new things to show how they're very similar to this. Are there any questions on that? Okay, so that's the end of your homework number 1 material. You have some basic mapping questions on there. Not a whole lot, but it's something you're definitely going to need to carry forward. In fact, you guys are going to do a whole electric field mapping lab in the coming weeks. So this is a little bit on homework 1, but planting the seed for the future as well.